Okay. Very good. So, okay, we're actually not starting, but we're continuing from tomorrow. From yesterday, sorry. Okay, I'm a little tired. Okay, so yesterday, the final thing that we have calculated was for the effective. How to our vertex. And this we wrote it as 3-dimensional polarization. One. Today, what we will do is we will calculate the total cross section for again the longitudinal photon in EIS, and then we will relate it to the structure function at that. And we will be using this effective vertex. So in this case, a diagram. This right here, I have gamma L coming in, I have here my quark anti-quark, and this is 0 and this is 1. And the first thing that we will do is to write the light from wave function for this guy by using the vertex that we calculated yesterday. So the wave function is written as the effective vertex divided by the energy denominator. For that, we will also use the relation that we found yesterday. So we're going to write it in terms of the option photon. So if I write it down, it would basically mean, okay, this guy. Plus minus plus this is my option photon, this is my quark, this is my anti-quark, so I have written down the energy denominator. I have the effective vertex that we calculated yesterday. So now, this guy, we know that we can simply write it as current 2K0 plus 2K1 plus delta H0 fine, and it might be minus H1. And then by using this three-dimensional delta function, I can rewrite the denominator. So the denominator, I would like to write it as, so let me write it like this. So here I have the numerator, which I will keep with the simplification. But then I'm going to write down the denominator in the following way. Then I can regroup the terms in the denominator, and I can write it again as numerator times two squared plus plus I just use the three-dimensional delta function in order to rewrite K1 third in terms of K0 and Q. And then I just regroup the terms, but then this guy, I can also write this one is in the third minus plus 1 plus 2 third. And this guy, we will call it as P-third, which is the vanillin invariant momentum. So with that, I can come back and I can still rewrite things a little bit more in a more organized way. So this is the then here is the 2 square plus minus 2 plus plus 2 square over plus. Just we wrote the denominator in terms of the linear momentum. But we regroup the terms. Then I can still factor out Q plus and K0, K1 plus in here. So let me just do it. Then it will be the same numerator here. It will here, and then on top of that, I will have minus 0 plus K1 plus 2 plus first plus 0 plus K1 plus 2 plus square. Nice. So now by using this wave function written in this way in terms of the linear momentum, we will use the optical theorem to calculate the total cross section. Then we're going to start with each plus for the first. And this will be written actually as the sum over the states, right, and the wave function that we calculated. Operator that I have inside is fine. First, so now everything is written in full momentum space. And the first thing that I would like to do is I'd like to go to the mixed space so that I can, when I'm writing down the actual iconal operator on the states, I will be able to write it in terms of the coordinates. So for that, we simply introduce the Fourier transforms. Now I have four. All these guys are written in the mixed space. It's a story now on time. Time. So now this is easy. We can simply just calculate this matrix element here. We know the action of the iconal operator on the D dagger and D dagger. We know that okay, when I act on this, they basically commute. So we'll go here, and then it will produce me a fundamental Wilson line, and then I will act with the same guy I'm sitting in here. It will give me a anti-fundamental Wilson line for the anti-quark, and then it will be acting on 0, which will give me 1. And then for 1 and the rest of this expression, I will just have to look at, I will consider the anti-quotation relations between D and D dagger and D and D dagger. And then at the end of the day, after some trivial stuff, some trivial calculation, we simply get to the point where we can open the game side. I have the 4 integrals. It's 0 for it's for phases. prime. And then from the commutation relations, obviously I'm going to get plus plus I have the two prime times still delta is 0. It's prime delta is 1 prime. And then I get delta of 1 prime minus and then the Wilson layer it's in the curve. That would be the expression that I'm. So it's basically nothing. We're just doing the anti-commutation. First calculating the action of this side and that, which would be the two fundamental and anti-fundamental Wilson lines. And then for the rest, we just do the anti-commutation between D0 and sorry, D and D bigger, and then D and D bigger. And then we get all these delta functions together with the deltas in the helicity. Okay, very good. So then now we can simply start writing down the whole thing, and using all the delta functions, we can simply integrate trivially over part of the integrals that we have. So at the end of the day, basically what we get is we still have the integrals that we cannot perform. Then we have the ratio of the color of 1 minus ratio of the color of 0 part. It's 1 part. By using, okay, so if we start using all the deltas for the helicity, at the end we get summation over the helicity 0, 1, because everything will be equal to each other, and this is going to be as 2, 1 is 2. Then I still have p squared, x squared, q squared, and now I have the integration. 0 plus we still have the deltas for the three momenta. It's 2 pi. I'm sorry, we use the two of them, transfer response from this from the longitudinal. Plus times the factors that we have are coming from this guy, which is 2.0 plus plus and then from the vertex we also have minus 2 plus 1 plus 2 plus squared times some integral, the transverse integral that I'm going to write down, and then we'll see how to calculate that, because okay, this is typical integral that we that we get all the time in these calculations. This is the third. Okay. So first, let us rewrite the, well, we can still do the integration over one of the longitudinal momenta by using this delta function. So if I do that, this guy will look like, okay, you can see this square, this square, I still keep the P5 delta become twice minus 2 then I have the two integrals x0, x1, and then 1 minus 1 LC, hence 0, x1. So this guy is the standard type of operator. And then I still have the integral over x0 plus over 2 count with x0 plus. But then if I do the integration, but for k1 plus, then I get another data function, which will be the q0 integral. That's one plus time minus 2 k0 plus 2 plus 0 plus over square times the transverse integral that I still have to calculate. Now at this point, we can rewrite this guy still in terms of by defining the Z0 and Z1. So Z0, Z0 plus Z1 plus. So if I do that, and then I still have this delta function. What is it? So it's okay. So I already used this guy, so which means okay, I can simply write this as Z as the bar. So this would be still plus by delta plus I'm going to type with NC square NC times alpha liquid. 0 1 2 8 1 times now I will look into the speed. Since I'm changing from 0, so this goes from 0 to 1 because of this data function. And then I have for q squared, z squared, 1 minus z squared times transverse integral. Okay, so if I calculate this transverse integral, you find I will be able to write down the total cross section. And for that, again, this integral, this transverse integral, is basically one of the integrals that one encountered with in all the calculations related with VIS. So, because of that reason, let me just like perform the integral for the people who do not recognize how to do it. So let me start here. So the integral is square was divided by e square plus 1 square 1 minus 3 h square. So usually people call this thing as h square. So this is the means and f changes mass depending on the flavor. So in this expression, remember the definition of PT. This is now 0 minus T per. So I can basically change the integration to T per from T0 to T per. I'll have T per to the I Z. Equal to 0. Minus that. Equal to 1. And I'm going to the I. Equal to 1. So in order to calculate this integral, now we will use the Schrödinger trick. So we introduce the Schrödinger parameter for the denominator. I can take this guy out, it doesn't depend on place. This is Concord. So now one from 0 to percent. So the next thing to do is to change the order of integrals, perform the PT integral first, and then let's see we have PT squared here, P per here, P per here, P per squared here, P per here, which means that we can simply complete the square, get a Gaussian integral, perform the Gaussian integral, and then whatever remains will be a remaining integral will be an integral over T.
Oh, sorry. So on the left, so in this integral, we say what is that in front of Q square?
This thing.
No, in front of Q square, is that H?
This is 4.
Oh, 4. Okay, sorry.
I'm sorry.
Actually, if you like the previous expression like for L square, I think you like the parentheses with the pluses. So I think it was parentheses to the square.
This one.
Yeah,
of course. Sorry, yes. But I'm trying to
yeah.
write fast. I'm sorry. But it's a good that okay. You guys are checking. Okay, so now let's finish this integral. I'll finish this integral. this integral. I have the paste it now. I have the that's this is the integral. 2 pi square into the minus t of t per square minus t minus pi minus 1 over t minus t square. This is 4. And then minus minus square. So this is what I had in the in here. So I just like put it to square so that I can perform the integration over G per by using the Gaussian integral. This is the part that I added and subtracted to make it into a complete square. And okay, this is what we have from the leftover from the Schwinger integral. So this integral is now it's already a square, so I can perform the integral over T per. It's a Gaussian integral. We know the result. So this is going to be strong. Now I do that comes from this T-per integral, and then the minus 40, and then so now I have to calculate this integral, but this integral we basically look at the integral book, we get the result. We know that okay, this any integral which is in this form from plus infinity e to power u minus 1 e to power minus e over t e to power minus c times t. This is equal to 2 times u over c power u over 2. So this k is the Bessel function. Whether it's 0, 1, it is basically defined in terms of the power of the integration variable t. And then this b and c will be the terms that are the coefficients of 1 over p and t that are sitting in the exponents. Okay, so by using that, now this integral L will reach into the So now, okay, now that we have all the ingredients, we have the, okay, I raised the expression, but we had written the expectation value of 1 minus SE up to this integral IL. So now we can just put everything together. And then through the optical theorem, write the total
Sorry, what's the first term on that expression? Is a sigma?
It's a signal.
Okay.
Yeah, total cross section. Scale. Intervals. 0x1. Right. Times integral over z. 1 0. So I can simply cancel those guys. They're sitting on both sides. And then I will have, so let me get rid of these guys. Here. And then the rest basically tells me the total cross section for longitudinally polarized DIS. And we also know that we can relate the total cross section to the structure function at L. And the definition and the way that they're related is very simple. So let's also write that down. I'm not going to write the expression for FL, but so total square So if I take out a factor of 2 pi square alpha m and q square from this expression, then the rest of this expression will give me the structure function. Very good. So this concludes my intended first lecture. So now we can go to the second one. So in the second lecture, basically what I would like to do is, first I would like to talk a little bit about the transverse dependent, transverse momentum dependent distributions, which are calculated in a completely different way. But then we also know that, okay, from the small x calculations, we can see the emergence of small x limit of some of the TMDs, depending on which process that we are looking at. So for that, and after talking about that and after calculating, so I'm going to pick the so-called wise equivalence TMD. The reason is because I would like to use this method, the wave function that we have calculated, to calculate the DIS digest production, and show that, okay, in some particular kinematics, we can basically see the emergence of this wise equivalence TMD from the small x calculations. So for that, let me remind you a couple of things. So for us, okay, what was appearing here in the dipole frame, in the dipole picture was the trace of UU dagger. So these are, again, UF is our Wilson line, which is this type ordered exponential. And a minus here is the like the background field. So if you do it like DIS on a dense target, it will basically define the blue background field of the target. And in the case for the target production, okay, the QQ bar pair will scatter on this background field. So if you want to calculate the IS target production again on a dense target, so we will basically end up with the dipole operator, and these dipole or quadrupole operators, so it depends. So the dipole operator is usually defined as 1 over MC raised with X bigger Y, but then it's T here. This basically means that okay, the dipole operator, once I have the trace of UU dagger, this operator, then I will have to average over the color configurations of the target. This thing here with the sub T basically defines that. It's like okay, how we write down the target averaging in the small x calculations or in general, okay, specifically more CGC. And if I want to, so I can write down the dipole operator in this way. If I have a quadrupole, it will be trace of 4 U's instead of 2. So it will be UU dagger. And if we, so for all kind of calculations that we do, if we don't want to do numerics, okay, like this is our result. But if we want to do numerics, we need to get some kind of model for these functions. So for the dipole function, usually people do, I don't know, GBW model, MV model. Actually, there are like experts in the audience who has done a lot of work on these things. But what I would like to say is that okay, from these non-perturbative objects in specific kinematics, we can get to the TMD. That's what I wanted to show now. But for that, let me start with the standard definition of the TMD. This is the operator definition of the TMD, and we will basically start manipulating it in order to put it in the way that we would like to see, which will come from the specific kinematics of the BIS target production. So this Y equivalence TMD, so this is the unpolarized TMD, but we will see that okay, if we do the BIS target, we will also not only probe the unpolarized Y equivalence TMD, but we will also probe the linearly polarized counterpart of the TMD. So these guys are written, so they are dependent on the momenta, transverse momenta, as well as X. X is small x is the longitudinal momentum fraction, and these are defined as integral over okay, so this is Xi. Xi minus momentum of the target minus component of the momentum of the target. X minus psi plus minus psi per times the average over the hadronic state of the trace at I minus psi plus so what is this guy here? This is, so I'm averaging over the hadronic states, hadronic state PA. If I minus are the minus I component of the field strength. And these guys here, this U plus, or this guy here, U plus dagger or U plus, are the gauge staples. So the difference between these guys and the Wilson lines are that Wilson lines are going from minus infinity to plus infinity, and these guys have finite range. So for example, this U plus is what is referred to as future point in staple. This is defined as start from plus to go to plus infinity for the third, and then come back from plus infinity to some plus third, and then it's Degler plus so these are the definitions, and if you look at it in the expert X plus plane, so this is my expert, this is my X plus expert. So this is 0 plus and 0 third. So with the future pointing gauge staple, it basically means that, okay, I start from 0 plus, I go to the plus infinity along this line, and then at infinity, I have the transverse gauge staple that comes to the point plus infinity plus and some transverse some e. And then from this place, so from plus infinity psi third, I come back to the psi plus and psi third. So this is basically my gauge state. So now the first thing that you should ask, okay, so you can see this guy here going from 0 to plus infinity. You can see this guy coming from plus infinity to psi plus, to given psi plus, but then you don't really see the transverse gauge link. And the reason for that is we can simply neglect it in the small x limit, because okay, the transverse gauge links are subiconal in powers of, if you start counting powers of energy. We are not going to use it, but also let me write down the past pointing statements. So in that case, we have printed as minus, and they're defined as 0 plus, so minus infinity plus 0 plus, and then and the dagger of it will be similar to this, but then it will be the other way around. And that one, yeah, I don't have any other pairs of chalk, but basically telling me, okay, for the past pointing gauge staple, I need to go back, I need to start from 0. I need to start from x plus equal to 0. I need to go back, go to the minus infinity. Then from minus infinity, I will go to the point at psi third. So there will be a similar transverse gauge limit. And then at that point, I will come back to the psi plus and psi third from minus infinity. So I'll come back to here. So in other words, okay, if you want, we can write like the gauge link is like a gauge loop as this guy times this guy. And then basically what will happen is, okay, so this will go like this here. Sorry, we need to take the big look at this one. And then from here, we'll go to minus infinity. And then from minus infinity, we will go to 0 transverse point. And then we will come back. And then we will have a staple gauge loop. So in order to understand this, now we are fine. Because, okay, the only thing that was kind of something that we didn't know was these gauge links. So now with the definition of of these staple gauge rings, we can simply go back and look at the, yes.
In the IS case, when you're
Uh-huh.
is the expectation value is also on PA, or is it in the vacuum? When you write expectation value?
Well, it depends. So if you're doing it on, like, if you're looking at DRS on a dense target on a nucleus,
Yeah.
then the expectation value will be taken for A, for the nucleus. So you need to average over the color configuration of the dense target.
Okay.
So that's how you will define your dipole.
For the F, what kind writing for the subscript?
Which one?
The-
This
Yes.
is y is equal to this, WW.
Oh.
Okay, so again, so this is the operator definition of the TMD. And apart from the, so in these, okay, in this definition, apart from the fact that, okay, we neglect well, okay. In this definition, we didn't neglect anything. But here, when I was writing the gauge staples, I neglected the transverse gauge links. And this is okay, one can justify this at the high energy limit, so there's no problem. So the next question is, okay, for the rest of the expression, okay, how can we take the small x limit of this? So in the small x limits, first thing that I would like to do is, so we usually assume translational invariance when we're doing the calculations in CGC. Of course, we don't have to, but this is one of the things, okay, that simplifies our life. It means that, okay, if I have like translational invariance, it means that the dipole that depends on point x and point y now only depends on the difference x minus y. So I'm going to use that in order to rewrite this TMD. And now from now on, I'm not going to write the WW because apparently it's not readable. So I'll just write F, and what I mean by F is the y-equivalence TMD. It's only specific for this guy. So basically, what I would like to do is I would like to rewrite this guy, this TMD. Let me write it as A of T in the following way, and then I will explain why I write it like this. So in order to go from here to here, maybe it's easier to go from here to there, because I used two things in order to write down this expression from the standard expression of the y-equivalence TMD. I used two things. I used the translational invariance, and I also used the fact that, okay, this normalization in hadronic states is equal to 3, 2 minus times delta 2. So if I plug this guy back in this expression and then undo the translational invariance, then I basically get back to this guy here. Of course, I need to shift because okay, you see here it's like from okay, like the points are defined at the transfer position xi, but the other transfer position is 0. So in order to write it in terms of x and y, obviously after doing this, I need to shift the things a little bit so that okay, it will start like one of the coordinates will be at 0 and the other one will be at x minus y. But this again is by using this and translational invariance. One can basically like go from here to there or from there to here. So they're in that sense they're equivalent. Now the other thing that I would like to say is that okay, in the small x limit in the CGC calculations, the averaging is PA, whatever I have inside PA, which is normalized by PA into PA. This guy here, this in the CGC, we write it as the operator inside, which is averaged over the color charges at x equal to xa. So at this given rapidity. Moreover, so this is one thing. This is the second thing. And then the third thing is that, okay, at iconal accuracy, if I want to calculate everything at iconal order, and if I don't care about the subiconal corrections, then basically this phase here, I can take it as 1. Because if I start expanding the space, the corrections that will come after 1, the corrections that will come will be subiconal corrections. So then the third thing that I will do is to take the phase minus take it to 1. Then with that, with all these things, I can now write down that the small x limit of y is equivalent to TMB, I can write it as d3 y is 5.3 third one is third, and then the phase of x I1 is equal to x equals y y. Now, in here, we can still realize something. So if I minus in the Light-Cone H, if I minus the point y is actually equal to bi and minus the point y. And then by remembering the definition of the standard Wilson lines, we can also see that okay, if I take the derivative of the Wilson line, sits at point y, then I can write it as equal to IG point minus dy plus u minus infinity to minus so again, you like the Wilson line it's an exponential. So if I want to, it's an exponential of the background field in mind. So if I want to take the transverse derivative of that, basically what happens is, okay, like I get inside the integral along y minus. So from minus infinity up to some point y plus and y third, it's the standard help of the Wilson line, let's say, or some kind of a gauge staple. And then at point y third, I have the derivative of the background field. And then from y plus infinity, I continue. So this is like how we can take the derivative of the Wilson lines. So now let me go back and let's look at this trace again. So this trace, if I write down the gauge staples explicitly, and this trace will be written as minus x. So this trace here is basically telling me that, okay, like I need to use the explicit expression of the gauge staples, but I know what they are, both for both of them. But in one case, I go to x plus to plus infinity point x third, and I come back to I come back from plus infinity to y plus at y third, and in the other one it's similar, y plus to plus infinity y third, and then plus infinity to x plus with x third. So so now I would like to kind of get connection between what is written here and the derivative of the Wilson lines, because at the end what I will get is the Wilson lines, and I would like to write them as derivative of the Wilson lines. But for that there's a slight problem, right? Because okay, we always go to, because everything here is future pointing. It means that we're always going to plus infinity. But in order to write things in terms of derivatives of the Wilson lines, we need to start from minus infinity and come back to a point, and then it can go from that point to plus infinity. But here, everything is written as some stuff that's going to plus infinity because all these guys are future pointing. So then, in order to able to get some connection, what I will do is I'm going to introduce here u dagger y, which is equal to 1. And in here, I'm going to introduce u dagger x ux. Now, if I do that, so this is equal to 1, this is equal to 1, this is still the same trace, there is no problem. But now, this trace, I will be able to write it as trace of u dagger x u from minus infinity x plus x third x plus x infinity x infinity third x infinity. Minus y So I introduce these guys. And then for the use that I introduced, I divided it from minus infinity to x plus and not from x plus to plus infinity. It's still the same. But the nice thing is that, okay, so if you look at these two guys, for example, so this is the gauge link that goes from x plus to plus infinity, but then it points x per. But then, okay, it also comes back from plus infinity to x plus at point x per, which means that, okay, it will go and come back along the same line, which means that, okay, this guy will be equal to 1. Same story goes for this one. This will be equal to 1. But then, okay, I'm already good because, okay, that's what I wanted. I wanted to have something in order to write things in terms of the derivatives of the Wilson line. I wanted to have something that was coming from minus infinity. And now, if I look at here, I have a Wilson line that's coming from minus infinity to x plus at point x per. Then I have the field strength insertion at point x per, which is exactly like here. And then I go from x plus to plus infinity at point x per, which means that, okay, this guy, I will be able to write it. This thing here, I will be able to write it as the derivative of the Wilson line from minus infinity to plus infinity at point x per. Same story is here for the y. So I come from minus infinity to y plus a transverse position y per. Then I have my insertion, and then from y plus I go to plus infinity again at the same point y per. So it means that by using the definition here, I can simply write down. I can write down the transfers, the TMD XA per as 4 over I G squared x per y per 2.3 times base over multiplied x x 1 So basically what I did, I realized that, okay, these guys from minus infinity to plus infinity minus, okay, like the field insertion at point x, and then from x plus to plus infinity, I simply said, okay, it will be written like this guy here, but there is integration over the plus component. So I already take the integration over the plus component from the definition here, and then this guy comes with a factor of IG square, IG. So I needed to divide my expression by IG. So at the end of the day, I can simply write this guy. I can take this I out. So this is going to be G squared, and there will be a minus here, and this is the small x limit of the y-equals TMD. Yes.
Shouldn't you swap U dagger X and U dagger Y? Maybe that's.
No. This is my definition. Well, one can. So you want to write. Oh, so you want to write.
The step above, you have UX dagger first.
Oh, yes, that is true. Actually, it's indeed, this is a mistake because, okay, I had like DIUX, U dagger Y, DIUY, then U dagger X. So this is true. This is Y, and this is X. This would make you happy.
Sorry.
No. It's true. So I was wrong. I wrote it. And okay, now it's consistent with my note.
In the circular line, so you are using the cyclic relation to
Mhm.
calculate the trend. So in front of the fxi minus, so
Mhm.
you have for u.
Mhm.
So you have u dagger x and
Mhm.
then there's u's.
Mhm.
So but in the first line, in front of fxi minus, so that's on the
No, but okay,
right.
in order, so from here to here, what I'm doing is I'm starting writing my trace from here.
Yeah.
So I have u dagger x,
Yeah.
then this ux, I'm writing it like I'm dividing it,
Oh, okay,
okay?
okay.
And then I have this guy. And then with that, okay, with this guy already divided, and then I have this guy here, which goes with point x, and then from x plus to plus infinity. So with this guy divided into two, okay, part of this guy and part of that one will give me one, as I say here.
Oh, okay, I see. So the US goes from negative infinity to infinity.
Yeah.
and divided. Okay, thank you.
Okay. Well, I don't have too much time, so I should probably hurry up a little bit. So basically, okay, so this is the definition of the Weiss-Equilibrium's TMD at small x. So now, how can we see the emergence of this guy with the PIS digit production? So PIS digit production, I will just write down the cross section. I'm not going to calculate that, we have already done it. But what I'd like to say is simply, okay, once I write it down, sigma, So if I write down what we have used, like everything that we covered before, and I want to write it for, so this is digit production. Okay, let me just write it. So this is a digit cross section, and in principle, okay, we can also do the color trace here, write it in terms of the quadrupoles and dipoles and ones. But in a minute, you will see why I just leave it like this. So now for this specific process, let's consider the kinetic regime where K0, like the two jets, the quark and anti-quark pair, K0 and K1, the transverse guys, they're similar to each other. So I would like to consider the case where K0, K1, the transverse momentum of the two guys that I produce is much larger than the total momentum of the two guys K0 plus K1. Well, in this case, there are two typical transfer scales that appear. So I will call it first one KT. So this is going to be the total momentum of the two produced guys. And then I will have some momentum PT. And this is, I will call it as direct momentum imbalance, and it will be Z1 K0 minus Z0 K1. So these are all transfers. I'm not writing the curves anymore. But in the limit, KT is much smaller than PT. Then it means that, okay, like the produced guys in momentum space, they're flying almost back to back, which basically corresponds in the transverse plane. It corresponds to small transverse size of the produced pair. So the relative distance in the transverse space in this limit, the relative distance between the quark and the anti-quark will be small. It's going to be R. And this thing, okay, this limit, we call it as a correlation limit. Well, okay, so in this limit, if I do this change of, if I consider KT and PT as my transverse momentum scales, then I can simply make this change of variable. So this is the first change of variable, and I would like to do the conjugate change of variable, which is going to be x0 minus x1. I will call it as R, and then z0 x0 plus z1 x1. I will call it as U. Now, in principle, okay, there is, okay, if you do this change of variables, if you go from K0, K1 to KT and PT and X0, X1 to R and B, with these guys, okay, there's Jacobian, but okay, Jacobian is like 1 over Z0 plus Z1, which means, okay, it's just equal to 1 because we have the delta function, so we really don't care about it. So then basically what I will do is I'm going to write K0 and K1 in terms of the KT and PT, and X0 and X1 in terms of R and B. In this expression here. And if I do that, so this will stay this part. And if I do this change of variable, go from 0 to 1 to 3 and P and 0 is 1 to R and B. And then the cross section, I will write it as equal R. Now the phases will become minus I T, R minus I prime, minus I T, V minus I prime, and then I will have 4 0 squared, 1 squared, 2 squared, 0 R and F, and 0 R prime. Times so you see, I did this change of variables everywhere except in the Wilson lines. So in the Wilson lines, if I do it, I will be able to write, for example, I of 0 is U of 2 plus Z1 times R. So X0 will be equal to this. But then, because of the fact that, okay, PT is conjugate to R and KT is conjugate to B, and KT is much larger, much smaller than PT, it basically means that, okay, my R is much smaller than my B, which is the small dipole size or the small transverse side, which means that I can perform Taylor expansion of this guy. The first non-trivial order, which is VD plus V1 or I. And I can do the same thing for U negative x1. U minus U R. And since minus U R. Now, obviously, okay, I will have to do the same thing for the prime coordinates, but okay, it's going to be exactly the same. But what really happens here is that you see then I can write down 1 minus 0 stable x1 as 1 minus B. Now plus Ri minus Ri 0 for the first term, that will cancel. I have DI times U dagger B, and then UB times DI U dagger B. So I would like to combine these guys, and it's also obvious that okay, this one can be written as DI UD of U dagger B, which will be exactly the structure that I have here. It comes with a minus sign, so this will flip sign. So I'll have Ri, DIUB, U dagger B, Z0 plus Z1, Z0 plus Z1 is equal to 1. So the expansion of this guy, the first order in R, will be Ri, DI, UB, U dagger B. So I do the same thing for the conjugate. Then I will get minus R prime J prime U dagger B. Now with this, I can go back and I can plug this expression back into here. And then it will basically give you something very simple. Minus 1 and R prime J. And then I will say So yeah, so basically what I did here is I simply take this guy and this guy, plug it back into my expression, and then it's also obvious here that okay, the integrals over R and R prime and the B and B prime are completely decoupled from each other. Then okay, this expression that's in the BB prime, you probably realize that okay, this is very similar to what we had for the small x limit of the Wise equivalence TMD, except now this is we did the calculation for the DIUB and DIUB prime, and here they're different, which basically means that okay, I can write down the delta ij part of it as an unintegrated, as an unpolarized Wise equivalence TMD, and the ij part will be the linearly polarized counterpart of that TMD. So this one is here. This is defined as minus Beuf square root 4. So this is the unpolarized, and this is the linearly polarized part of the TMD. The last thing to do is perform the R and R prime integrals, but these integrals can be written by using the definition of K0. The integral definition of K0, we have this is equal to a to q over 2 pi squared e to the minus I r for 2 squared plus Beuf squared. So one can use this, the definition, put it back in here, and then change the order of integrations, perform the integral over R and R prime separately, and then at the end of the day, basically what we will get is the TMD factorized formula for BIS budget production, which is going to be the last thing we're writing here. This is alpha S. So this is the correlation limit of the BIS budget production calculated from CGC, where we have seen the emergence of the linearly unpolarized and linearly polarized Wise equivalence TMDs. One final thing that I would like to say, some people actually likes to introduce the angle phi. This is the angle between GT and PT. Then in that case, you can write I J over J as Then in that case, you can simply replace this guy and write it as alpha this. Okay. This is the final formula. So basically what we have seen is, okay, by calculating the correlation limit of the various target production, we were able to get the TMDs, bioequivalence TMDs from this expression. And actually I'm done, but there's one thing that I would like to say. I'm not going to write anything, but simply, okay, when we were doing this calculation, we were calculating the correlation limit to first order in R, in the amplitude and in the complex conjugate amplitude. Which means that, okay, the hard factor, okay, these guys in the TMD factorization, these guys are called as hard factor. And these are the POLs. So if one wants to calculate not the first order in R, but the second order, the third order, and if you go ahead and calculate all these corrections, then one can actually resum those corrections, and those corrections will come as corrections to the hard factor to all powers of, so those guys will be powers of NT or NT. And if you calculate order n, and if you do the resummation, then basically you will get from the TMD factorization to what's called as ITMD factorization. It's like the small x improved TMD factorization. So that's one thing. And then for the case of TMDs, we can also calculate the corrections that goes as QS over PT. So this is the leading term. This would be the leading term in powers of test. But then, okay, if I want to calculate the QS over PT corrections to the TMD, then I can basically go back to the whole CGC result, the whole small x calculation. Okay, so that's all I wanted to say. Thank you. Thank you very much.
So, questions? I don't see any. So any question from the people, from the 4 people online? Okay. I don't see any, so
Okay.
we're just saying Tolga again.
Thank you very much.